Thank you for joining me. My name is Christopher O'Hara, and today I will be presenting a robotic platform and Materiomics approach for developing synthetic and alternative skin replacements. So the general or high-level idea is that I want to take humanoid type robotics that have been developed or could be developed that contain mostly kind of structural skeletons and use this to develop and test out the synthetic alternative skin replacements. So next I will show the agenda, which follows the typical structure. We have the introduction, which is today is going to be mostly the organ description, which is going to be skin, the problem description and the demand, current approaches, the proposed approach that I'm addressing, and then a comparison, which includes a brief bit of kind of discussion, and then the bibliography. So skin, we're already quite familiar with skin. But it is the largest organ in the body, accounting for approximately 50% of the total mass of an individual. And if you lay this out, it's about 20 square feet. Skin contains three primary layers, the epidermis, dermis, and hypodermis. Because of the large amount of surface area and it's the initial barrier to protect us against things like sun and chemicals, it's really susceptible to damage and prone to disease, including cancers. And then the biological mechanisms reduce the skin's natural repair capabilities as we age. So the older we get, the less our skin is able to self-repair and or repair back the way it was as compared to when we were younger. So this is mostly a recap of what we already have learned and covered. So some additional the demand, or why do we need this type of solution? Is because every year in the US, approximately 1.1 burn injuries require medical attention, and these are just the ones that are recorded, which indicates that approximately every 23 minutes there's a burn accident. Now, not all of the burn accidents are severe, but if you actually take the cost and you split this over all the different individuals, so the treatment cost over N, where N is the number of individuals, the mean burn treatment cost for high income countries is approximately 88,000. So somewhere like the U.S., where the treatments might range from $700 to $700,000. When you look at the mean value, it's quite high. Now, another a big threat to our skin is skin cancer. It's the most common form of cancer, actually, and annually 4.9 million people were treated. Actually, this is as of 2011. With the treatment cost being about $8.1 billion. So Guy et al. Looked at some analysis for this between 2007 and 2011, and they found that every year the cost increases about to 125%. So meaning that skin cancer treatment is also one of the cancer treatments that actually gets more expensive over time as compared to some of the other ones. So for both of these problems, grafting is a solution, and there's more problems, but we're going to focus on these for now. Grafting is a solution, but 30% of up to 30% of these grafting procedures fail and require regrafting. And when this happens, the cost at least doubles the long-term cost because we actually have to fix the damage. There might be infection, inflammation, or irritation. And these, the graft failure itself can be caused by the initial graft not adhering properly. So either this biological or biocompatibility rejection, or just the actual interfacing. So the alignment wasn't proper, or simple movement. We even move around in our sleep, but simple movements could actually damage the interface of where the adhesion is supposed to take place. Because humans are dynamic beings, when we walk around or when we move, we need to try to find a way to address this. So the current solutions related to skin grafting, when we look at the historical or conventional approach, we would take a transplant skin from one part of the body to another. So it might be somewhere like taking skin from the thigh or buttocks and moving it to a large or deep open wound on the arm or the face. But this is not optimal because the allocation creates another wound, right? We're going to cut the skin from one area and move it. So infection can occur at both locations, actually, and it's just not the best case. Over time, we did develop more modern solutions using artificial or synthetic skin alternatives. And these can range from just approaching the dermis, like the dermagraft, or multiple layers, like Integra, I'm not going to go into too much detail about these because we covered them in class. But the idea is that we do have solutions for grafting and autografting. And we can also have some solutions based on adult stem cells, or donor-based cell lines, where we take some of the initial cells that we have in our body, and we culture them, and then we actually can develop our skin replacements based on this. Irregardless, both of these options, they still incur risk regarded to infection and rejection, with even some synthetic grafting techniques that can lead to cancer. So it was observed for some of the basal treatments that it wasn't clear why. It's not clear if it's the material or the procedure, but actually getting skin grafting can lead to cancers at the interface. And so some of the biggest issues are also related to testing the skin before application, because we move in a dynamic way. We also have mechanical loads. These type of stretching and these behaviors, we need to be able to test them. And if the skin replacement is in a static location, that's not possible. So my proposed solution is to build a robotic platform for growing, testing, and analyzing the skin alternatives. That general concept is we take this robotic skeletal structure, you can see some examples in the bottom left and the bottom right, and build skin layers, the tissue layer on top of it. So this will allow us to account for dynamic movements and load-bearing activities, as these robots, they have a full dynamic range of motion, and also can carry weights up to approximately 20 kilograms. If you look at the Kingaro picture at the bottom right, you can actually see that they have, it well represents some of the movements that humans can do. Also, these robots have been developed in a modular or adjustable way, so you can switch out some of the components. And another nice thing is that because of the kind of open structure that we can have, we can actually analyze the inside or the hypodermis side of the tissue that we're generating. Also for these robots, they've actually generally created the skeletal structure, the tendons, and the muscles, and the way they behave, and the way they actually act to the type of electrical responses or mechanical responses, but they haven't actually tried to do the skin for these. So secondarily, the skin itself, right? I think the best approach would be to develop or utilize a personalizable acellular dermal regeneration template, or DRT. So the idea would be that we have some type of DRT that we develop, and we take a non-porous sheet to separate the DRT from the skeletal structure to prevent some unintentional damage or leaking and contaminants. And we combine this with some 3D printing of biomaterials onto the DRT, where we are concerned with the vascularization or the epithelialization of the blood vessels inside the actual skin that we're developing. We could use natural materials like collagen or fibronectin for the scaffolding, but we could also use polymer-based solutions if we want. Another nice thing is we could customize the dimensions of the skin itself. So this might be the area that we're actually addressing, or even to personalizable things like the skin tone. So this does matter for some individuals who want to try to have the final product look similar to our real skin. Lastly, we could utilize stem cells or cell isolation from a donor, where we take the cells from the donor and actually generate our new skin cells from this. The image at the bottom actually shows the general DRT process. We start with some microcarriers and an immature extracellular matrix, and we have some embedded human fibroblast. We take this and we mature it in a maturation chamber, or mold it in there. We have some media flow, so some different cultures flow through it, and our ECM is assembling. And the final result should have some type of endogenous human dermis type behavior, where we have the vascularization, where the blood vessels themselves have been kind of developed, or the network for this is developed inside the skin alternative we're making. But we also care about the epithelialization. How is it going to interface with our blood vessels that we have currently in our body? Another motivation for me to design like this is the skin on a chip. So we have different layers in our body, and the idea is that we could replicate this with the skin approach that we're taking. So we have in the image, you can see at the top, we have an epilayer or the epidermis. The middle is the dermis layer and the bottom is the hypodermis. Between these different layers, we have some porous type, it looks like a silicon wafer that has holes in it. You actually use this for the interconnectivity of the different layers. You can send the materials, the nutrients, or the cellular signals and growth factors to each of the different layers. And this is done by, if you see the image on the right, there's these via or through holes that we have. You can actually add the materials or the information that you need there, or analyze the deltas between the differences between the two, the input and the output. Finally, for the proposed solution, I also want to consider something called a soft robotic dressing. And this could be either an enclosed synthetic tissue or a cell-laden hydrogel. I don't really have a good name for this yet, except that basically I want to make a layer that goes on top of the epidermis to provide the encapsulation of moisture, encourage growth, protect against contaminants, or even supply some nutrients like growth factors if it's appropriate. And this will act as a bioreactor for the basically this entire assembly I'm talking about will act as a bioreactor for the skin organ development. And we can develop this in the excuse me, in the lab. The picture on the bottom, on the left side, this actually shows a type of a soft robotic hydrogel that was used to make muscle scripts. And there's a beam at the top, and basically what happens is they apply a voltage, and then the muscle script itself can react to it, so they can actually get some mechanical or electrical behavior from this muscle script that has been developed with natural materials like collagen and things like this. The image on the right actually tries to demonstrate that with the electrical field, this actually acts as what they call a biobot, or it's basically a micro or nano robot with this muscle script. And what happens is, as an electrode, as you apply voltage across it or electrical field across it, you get some type of response. So the reason I included this is because basically what I want to be able to do is add this epi layer on the very top, where we can do some analysis, some actually checking of the mechanical distribution from stress and strain, or elemental type of impacts on the skin. So in comparison, up until now, such a robotic platform for growing synthetic skin does not exist. And only recently in 2017 did anyone actually kind of discuss the functional or developmental requirements. However, they were still very loosely defined. There's nothing quantitative at all. Even the qualitative aspects are on the level of we should care about the interfaces, we should care about the stress and strain. So similar to what I discussed today, actually maybe in less detail. Two high-level considerations I have are that this approach will be provide a safe environment for growing the skin substitute in vitro. It's also providing an environment for testing the stress and strain under dynamic motions and variable loads. And these are the core things that I think we can take away. I would also like to expand it into this, incorporate more material omics, because I think we have an opportunity to do so. Here we can embed some interconnected electrical or chemical networks that can measure like location-based analytes. So basically, maybe you want to measure the O2 concentration or the temperature, the stress and strain in a certain area. We could actually generate kind of like we know the nerve network or a blood vessel network. We have another network that's actually just used for collecting telemetry. Here we can also do the computational signal or physiochemical, electrical, morphological type of signal monitoring and analysis, and observe how the material works under stress and strain or under different conditions. And it could be including temperature, humidity, these type of things. The 3D environmental modeling. So how does this material compress? Is there shearing? I also think we can incorporate or embed smart materials. So embedding smart materials within the skin alternative would allow us to do some type of novel kind of some what's it called biomodifications, or just adding them to the top of the material. We can collect sensory data or telemetry data. And then finally, we can model the interactions between cells, organs, and simulated systems. Where modeling on top of this skeletal system, we have access to the hypolayer at the bottom, we can actually find out what is the tension or the pressure, what are the things that we need to care about in moving forward, or maybe even understand the human body better. Of course, the primary limitation is it's kind of unclear if such an ambitious goal is possible. So we would need to take a piecewise approach to this to find out if it's feasible. And however, I want to note that I've tried to describe and design this system in a way that's completely interoperable. So my goal here, or my motivation, is that instead of just specifying earlier in my proposed solution that this is the mass and the surface area and these are the absolute materials we will use, I want to be able to incorporate many different techniques. It could be 3D bioprinting or injection molding. It could be synthetic or natural materials. We could use hydrogels on the top, or the idea, the core takeaways that the problem I want to solve is the actual dynamic modeling, or the dynamic loads and stresses that are applied to a skin, and basically use this robotic platform as a way to analyze and verify and validate these before trying to actually adhere them or transplant them to a person. So I think that being open-ended or being open-minded about this is better. Having a high level of abstraction is more important for this type of approach, this architectural approach, than specific low-level details. These are my references. If you want access to any of them, I have them. I can post them in the comments. And I want to thank you for your time. I look forward to your questions and your discussion. And if you have any, if you have any questions, please let me know. Thank you.